Hello everyone, good evening. Welcome back to the session 9. I hope all of you are doing good and keeping yourselves safe. So in the last session, we actually discussed about convolution neural networks, CNNs in short. So we discussed about how we could actually build a convolution neural network ourselves by using a TensorFlow, TensorFlow 2.0 actually. And we actually did a basic coding question on CNN as well. We built our own CNN and we saw how CNN performs and why is it uh, gaining a different advantage over other image classification systems. So we also discussed about transfer learning and we discussed the concepts of ResNet and VGG16, but we did not code that thing up. Also, I told you the last lecture that today we'll be building a complete project based on all of the learned classes and we will code this up together. So here we are with a new challenge, which is known as a food classification challenge. So this is actually based on a data set called Food 101. So this data set is publicly available and you could do a Google search to know more about this data set. So I will just quickly walk you through the agenda for this particular session so that we are already ensure what we are going to do. So first we'll start with the project description, that is our dataset description. We will then like code up the entire thing up, like we will code up the CNN thing up, the resonant thing up, and all of that, and then we'll come on to the results. And while coming on to the results, we will discuss like why did we select this particular model only with these number of parameters. So this is all about our approach. And finally, we'll also give a brief idea on what our thoughts should be while we are building anything similar and what should strike our mind at the first in case we are doing an image classification problem. As an experiment, as I've already told you, we'll be coding this thing up entirely on our own. We will get to know CNN better. I mean, while building, like while working on the code, we will get to know more about CNNs and transfer learning in general. We will see how to evaluate the results, how to plot the graphs, how to use TensorFlow, like even better. I know you all have a good idea of how to use that, but building a real life project actually helps you do that. So Food 101 is a very good data set to get started with. Like a lot of research has been done on Food 101 and a lot of research paper has been written as well to improve the state of art for this model. But we are not concerning ourselves with that in this point in time because our major goal is learning things and not like getting like the highest accuracy possible. Obviously, we'll try to achieve as high as accuracy as possible, but ultimately our goal is on learning. So as I've already told you, we'll be using this dataset called Food 101 dataset. So this Food 101 dataset contains images of 101 different varieties of foods. So as you can all understand, the goal is to identify, given an image, we have to predict what class does this image belongs to. Obviously, the image will be of a given food. So suppose, let's say after training the model, I have been given an image of hamburger. So my model should correctly predict if this image is an image of hamburger or is it an image of sushi or something else. So I hope you understand the goal is to predict, given an image, what class will the image belongs to. However, a quick note, since training on 101 different classes is like very computationally expensive, very computationally expensive, and I understand a lot of you won't have access to GPUs because again a GPU is required while training convolutional neural networks. However, you could also use Google Colab as well, and I'll be using Google Colab for this specific lecture. But again, Google Colab has its own limitation because you cannot hold a lot of memory in Google Colab, and so one-on-one training on 101 different classes is like not entirely possible. So what I have done is that I have actually taken this data set, broke this data set into a smaller subset of 7 classes. So that means instead of having 101 classes, we have only 7 classes, and we'll be training our model on this 7 classes only. So and at last, we will also hold this deep learning. We will also host this deep learning model on our Flask server. It can be a Django server as well. Depends on what we're trying to achieve. But the goal is to actually like host this system. I mean, host this model onto a local server. And once that has been fixed on our local server and is working fine, we will also go ahead and host it on Heroku or any other SaaS platform as well, right? So as I've already told you earlier before, hosting a machine learning model is equally important as building a machine learning model, because at the end of the day, you will have to at the end of the day, some new user or some other user will actually use your model. So it's not like you are going to use that, it's someone other or someone from the crowd who's going to use it. So we have to learn hosting as well. So that is why this point is particularly essential. However, I don't know if this is completely possible in this lecture only, I mean session 9 only. If it's not, we will move this part to session 10, I mean the hosting part to session 10, and we can cover it up from there. So let me just tell you what our approach to problem will be. So we'll first building up a very basic CNN model, and in our very basic CNN model, we'll discuss how the architecture of CNN would look like. Then we'll do some hyperparameter tuning in this CNN model. Like we could actually use some image augmentation and all of that stuff, rescaling factor and these stuffs. So and we can check by increasing the number of filters as well to see if our CNN model performs better or not. Because I've already worked on this problem, I will give you a quick hint that CNN is not the best approach to this problem, because as I've told you, it's a computationally heavy data set. So at the end of the day, we will be moving on to a transfer learning model only, and that transfer learning model will be ResNet 50. So we'll be seeing like how ResNet 50 performs better than CNN for this particular question. And then, like as I have told you, we will then save the model using our HDF5 model format, and then we could actually use it while hosting it on different local hosts / web servers. So this will be our approach to a specific problem, and this is not the end of the session. I mean, this is what our approach to problem looks like. But before starting this session, as I have already told you that I have already made this, or I have already worked on this. So I will give you a quick heads up on what our final project will look like once we have built this thing up. I mean, entirely coded this thing up. So let me just give you a quick video recap over here. I mean, I already have a video recorded in place for this. So let's see. So here I will select an image, and this will give me like in what category the image falls like. So just see this video for a short time. Just stopping the video over here, I guess you would have got an idea of what we are trying to achieve. I'm not saying that we will do this in one lecture itself, but this will take some of our time. But yes, the final result will look something like this. Obviously, you can change the HTML and CSS part on your own. You could try to make it even better. I'm not good with front-end part, so maybe it's not the best looking website, but this works, and this is how exactly a machine learning model is hosted on a website. I have hosted it on a local server, but this is what this looks like when you host it on a website as well. So I guess this has made you more interested in learning and coding this thing up. So without much of our time on this, let's get started then. So as I have already told you, I will be using Google Colab for this particular session. But before working on Google Colab, let me give you an overview of how our dataset looks like. So because it's a CNN model, I hope you know that while while we are on CNN model, we require something like a test directory and a train directory, right? So we already have divided this into a test directory and a train directory. Meanwhile, if you go to the train directory, you will see that we have 7 different classes for a train directory. This is chicken wings, then there is fried rice, then there is hamburger, then there is ice cream, pizza, ramen, and sushi, right? And all of these contains like images of this particular category of food. So this is how a folder structure should look like, and in case it does not, we have to amend it to make our folder structure look like. However, in this dataset, this folder structure was already like this, so I did not have an extra work to do. And similarly, for our test directory, it would be something like this one. All right, so this is how our data structure basically looks like. Again, like since I'm not using my local environment and I'm using a cloud environment called Google Colab, so obviously I have to find out a way to like somehow establish a connection between the cloud computer and my desktop. So what I had done over here is that I've actually uploaded this folder as a zip file to my Google Drive, and I will be connecting my Google Colab to this Google Drive, and then we can like unzip everything and work on it. So again, a lot of new concepts to learn, like connecting Google Colab with your Google Drive, extracting out, reading out zip files and extracting these things, which we called as like in technical terms, we call this as steps before data processing, pre-processing. Something around that sort, around the same lines, but a lot to learn. So without wasting much of our time on this, let's get started. So first thing first, I need to, as I told you, I need to connect my Google Colab to my Google Drive, right? So what I will do is I will write a particular line over here, which is from google.colab import drive, right? And the next line will be drive dot mount, and here in commas I will write content slash drive. So this is something you need to remember. Not remember, but this comes from experience. Like as long as you practice, or if you practice this thing many times, you will actually know like how to connect your Google Drive with your Google Colab. So this is nothing to worry about. Like this comes with practice. You could actually search on it on internet to get to know how to connect with Google Colab to Google Drive. But anyhow, we are working on this, and so I will run this or execute this particular cell. And once I have executed this particular cell, so it will take some time for the first run. Also, we need to follow an additional step. So once it runs, let me just tell you that what that additional step is. Okay, what I will do is I will actually just pause the execution for a second for the statement over here, because that additional step is necessary. So before working with anything related to like CNNs, the first step that I prefer to do is changing the runtime to what we call it as GPU, right? GPU is graphical processing unit. So it's very much important that we use GPU for faster training. And I could have done that after as well, but I prefer to do it before, because this will save us a lot of time from future trouble. So just save this over here, and it's in runtime followed by change runtime, and then use GPU, right? And now just run this piece of code again. So it will again take a second to run your first cell, and once that is done, once the runtime environment is basically set up, we could actually move ahead. So it tells me go to this URL in the browser and enter your authentication code. So I will need to sign in because I am on an incognito mode. So okay, it's already signed in for me because I have already used that to open my Google Colab. I will just copy this over here, and I will just paste the authentication code over here, right? And once that authentication code is pasted, so it will give me like success. It will not give me success, but I could see that it will tell me mounted at content/drive. Now, how we will know that if our file or if our drive is essentially connected to our Google Colab or not? So click on this folder structure over here, the folder structure that you could see, and over here you would see something like drive. Click on this button over here, and then you would see something like my drive. So it's my drive is appearing over over this folder over here. So this means that your folder structure is in place. So I have all of these files stored over here. So this means my Google Drive or is connected to the my Google Colab, right? So once this is connected, so now what I will do is now I have like something called I have stored this food 101 dataset, as I have told you, in a zip file. So I will need to find like where my zip file actually resides in my Google Drive. So I will go back and I actually know where it is. So as you can see, this is food 1017 classes.zip is the zip file that I am looking forward to, already hosted on my Google Drive, right? So now, since it's a zip file, so what I will need to do is I will need to extract this, right? Like it's a zip file, so we cannot work directly with zip files, so we will need to extract that. So again, extracting a zip file is very easy in Python. So there are different libraries in place, and this library is called import zip file. This library is called zip file. So I will just import a zip file from over here, and once zip file is imported, what I will do is that I will read this zip file and extract it. So I will write with zip file dot zip file. It's like you are importing zip file, capital zip file, from zip file, which is the name of the module. And over here, I have to pass in the path to my directory, or the path to where my folder or my file is actually stored. So I will click on these three dots and I will click on copy path, and I will paste this over here, and I will open this in read mode, right? Because I'm reading this and I'm not making any changes to it. And I will give it an alias name as zip underscore ref, right? And once this is done, what I will do is I will write zip underscore ref dot, zip underscore, it should be zip underscore ref dot extract all. Okay. And once this is done, I will just run this piece of code over here. It tells me there is no module named zip file. Okay, so this should be a capital F and not a small f. So we need to take all of these things into account while working with this. And as you can see, it's progressing over here, and will take some time. And once this is done, this will give you a success. So since it has executed without any errors, we basically know that okay, my zip file is extracted. But where is my zip file extracted? So since I had not given any location to where my zip file would be extracted, so this is directly extracted into my Google Colab and not Google Drive. In case you wanted to extract it into Google Drive, you could have actually like given a path over here, like the path to Google Drive over here, and that would have extracted into Google Drive. But I do not want that, because I know there are some definite issues while writing files using Colab to Google Drive. So that is why I have directly imported to Google Drive, so that the same ecosystem is there in place. So what I will now do is, like, let us see if it's extracted, if it's really extracted or not, or it's just something that we did not get any error and like it's not extracted. So what I will do is I will go back over here, just press this button over here and go back, and okay, just give me a second to figure this out. Should be there. Okay. So, just give me a second now. I guess by mistake I did point out to a different directory, but anyways, we are now sorted. So actually that opened the complete root directory in itself, but I know that was in my content file. So as you can see, like we were actually using the drive thing. I mean, we were actually using, when we were working with Google Drive, we were actually using the drive thing. But now you can see we have this folder called food101_7 classes, right? And just dismiss this. And this food101_7 classes is what we have extracted out. So if I just enable this view, so you would see we have the same thing that I have given an overview of. This is called the train directory, and there is a directory called the test directory. So the train directory actually has these 7 different classes. The test directory also has these 7 different classes present as well. So we are all good to go as our files have been extracted out. All right. So now what we'll do is we'll now require the three very basic machine learning libraries, because they are required every time. And I hope you're already aware of what these libraries are. These are NumPy, Pandas, and Matplotlib. So I will just import NumPy as NP and then import Pandas as PD, and then import matplotlib.pyplot lib.pyplot as PLT. All right. So this will basically work. And the only down advantage with, or the disadvantage with Google Colab is that you have to manually press on this plus code to actually like add cells in your like notebook. Otherwise, what happens in Jupyter Notebook is that as soon as you execute this particular cell, a blank cell would actually like come down. But it does not happen with Google Colab that way, and you have to manually click on that to get it working. But anyways, it should not be a hindrance to any of our tasks. And now once we have imported these 3 libraries, we will now import the most important library for deep learning, which is called TensorFlow. And this is where your deep learning modules are stored. So import TensorFlow as TF. And once TensorFlow is important, what I could do is like I could actually use a random seed. So I might or might not use a random seed. I'm just commenting it out over here. Like we can use a random seed if we want to reproduce the output. So what that means is like let's suppose you run this code on your system, right? You run this code on your system, and now you run this code on your friend's system. So obviously what will happen is that the shuffling of the data set that will happen, because there are random parameters in all of the TensorFlow libraries. So the shuffling of the TensorFlow, if it happens anytime, you're not sure if you will be using the same shuffling as that was there in your friends, as that was there in your system or not. So even if you execute the same code on your system and your friend's system, so the output might be a little bit different than what you are expecting. So in case you are expecting it to be like same in both of these cases, we have to use a random seed. So what random seed would do is that it would actually like enable you to reproduce the output over different systems. So if you want that, like you could use something like tf dot random seed and then pass in a random seed value. So tf dot random underscore seed underscore 42 is like what we generally like to use, but again, it's your choice. I won't be using that because I don't want to reproduce this output, but in case you do, you can like do this, right? So maybe just comment this line out for your reference, and you could use this. Okay, so something like this, and then I will execute this piece of code. Okay, now this piece of code is executed for us. All right, so our the very basic steps of our preparations have been done. All right, I mean, we have actually covered on how to read the data set from our Google Drive, extracting that, importing the basic libraries, TensorFlow, and all of that kind of thing. And we have done that. So what we will do is now code those things up. So I do see one question in the chat box. However, like I will answer this when the time comes. Don't worry, all your questions will be answered. And okay, so now let's get started with the actual coding part. All right, so for the actual coding part, now our goal is to do something that we could actually read the images, right? So in case if there was a data set, we could actually directly use pandas.read_csv, and we could actually read the complete data set. But this is an image data set, and it is divided into different folders. So we need to do something so that we could actually read and iterate over these images. So again, TensorFlow makes this task very easy for us to use. So what I will do is I will just write train_data gen is equals to tf.keras dot pre-processing dot image data generator, right? So what this will do is, as you can see, this is already open me the prototype of the function, like what the function would actually look like. So here, as you can see, there are certain parameters, like there is a parameter called feature-wise center, sample center, feature-wise normalize, and all of that thing. So this is not necessary that we will use everything over here, but these are some of the parameters that you could use. So I will only use one parameter at this point in time, which is called rescale. And rescaling is basically like I will be converting all of the pixels of the images to between 0 and 1. So as you know, every image consists of different pixels, which are divided into categories like RGB, since image is in RGB format. So, and these pixels like are ranges between 1 to 255. But since normalizing works better, this has been proven in CNN that once you rescale your image to between 0 and 1, pixel values between 0 and 1, things work better, because at the end of the day, you're normalizing a data set, and so you are actually basically like reducing the values that the values need to be trained, right? Earlier it was like somewhere that there was a value called 64, then there was a value called 128, but now every value is between 0 and 1. So computationally it's very less expensive as well, right? And we have done this for training for the training data set, and similarly we will need to do this for the test data gen as well. So test data gen is tf.keras dot pre-processing dot image data generator, and then again rescale is equals to 1 by 255. I hope this is clear to you that we are just rescaling the images over here. And so I will just run this piece of code. Should be executed without any fault, and so it has. So now we have rescaled our image, and now what we need to do is that we need to iterate over our every image, right? Iterate over the image of both the test and the training directory. So for that, what I will do is I will just write train_directory is equals to image data gen actually tf.keras dot pre-processing. Okay, so okay, we already have something called we already have stored this in the variable called train data gen. So what we could do is train_data gen dot flow from directory. If we had not stored that in our variable, then we have to do the complete, then we would have to write the complete sentence. But since we have stored this in the variable itself, so I could actually call the variable and then use flow from directory. So this flow from directory will actually take the directory name and some more parameters. And as you can see, like it has again opened the function prototype for me. So the first prototype is directory, like where our image directory is stored or our training directory is stored. Then it will take a target size, like by default it's 256,256. However, we could change it. Then there is a thing called class mode, and then there is a thing called batch size as well. So there are other arguments to the functions as well, but that is not necessary for us at this point in time. In case it is, we will actually come back and see like what it looks like. All right, so train directory is equals to train datagen dot flow form directory, and now we have to give in the directory, I mean the path where our training data set is. So our training data set is here, like in the train directory. So I will just use copy path, and I will use something like just give me a second. I will use something like this, and once this is done, now it tells me like I have to give one target size, right? So what I will do is I will use target underscore size, and the target underscore size that we'll be using is called I mean that will be 224 comma 224. We could have you, I mean it's on you what you want to use. However, 224 is a good thing to start with. And then what I will do is I will write class mode is categorical. Even if I would not have written it, things would have been fine because that is by default. But anyways, let's just write it. And then the batch size is 32. Again, these are the parameters you could, I mean, you could actually change by yourself if you want, and this depends on your expertise. But since we're just starting out, I am just going with the default values because these default values have been enabled or have been given in the function prototype after making or after seeing a lot of practicals. So works well under certain circumstances, however not always the case. So I just copied the same line over here again, but what I will do is that I will do it from test directory this time, right? So test directory is equals to test directory or test datagen dot flow from directory, and instead of train, this should be test over here, changing the names because I know where it is stored, and then the other thing would be absolutely same. And I will just run this. So as you can see, it has given me an output that says it has found 5,250 images belonging to 7 classes, and it has found again 1,750 images belonging to these class, I mean the testing classes, right? So you see like this train detergent, like the chicken wings, fried rice, hamburger, ice cream, pizza, rice, ramen, and sushi. So these are the 7 classes, and in total there are 5,250 images. And in the test directory, again they are the same classes, like there is chicken wings, fried rice, hamburger, ice cream, pizza, ramen, sushi, and ramen and sushi. So I guess the classes are same. Let me just check. Ice cream, pizza, ramen, yeah, sushi, yeah. So these again contain 1,750 images. So if you see the ratio between them, like can you just calculate the ratio between them? I guess that should be something around 1:3 or 3:1. That is between training and testing dataset. So 3:1 is a good ratio to start with. So what that means is that our data set, I mean, we will be training this on like 5,250 images and testing our data set on 1,750 images. So what does testing mean? Testing means over here is that we already know which category does this food belongs to, but we will actually treat it like we don't know to what category does it belong to. I mean, we will treat it as an unclassified input, unclassified output, and we will just take the input from it. And based on the input received, we will get a certain output, and then we will compare the two outputs together. That is the output received and the output it should be. And so if that is same, we will if that is same, we will actually increment our counter that, okay, we have got 1 correct, we have got 2 correct, and something of that sort. And if it's not the same, we will keep the counter as it is. So in classic, I mean, in terms of machine learning / deep learning, we call this like using confusion matrix to predict like how our data set actually works. But since TensorFlow gives you an accuracy at the end of the training epoch itself, so I mean, so you don't need to calculate it definitely, but again, it's a good idea to check like what actually happens. So this is what our this is what we need to do before actually creating our TensorFlow CNN model. So now once we are done with this, we will now create our first model. So as you can see, I'm actually receiving like warnings from Google Colab that my GPU is not utilized because till now I have not made my model. And since it's a shared platform, I mean shared cloud platform. So they always ask you, if you are not using the GPU, just turn it off so that other people could use it. So it's a good idea. If you're not using GPU, turn it off. But since I'm using this at this point in time, so I won't turn it off. So yeah, so now model 1 is equal to tf.keras.sequential, and over here we have to pass in something, I mean tf.keras.sequential, and we now have to like pass certain inputs, like we'll first start with um, a convolution layer. So I hope you remember what the basic structure of our convolution layer, I mean a convolution layer is. We first start with a basic conv 2D layer, and once we are started with the basic conv 2D layer, we then have a max pool 2D layer in place, and we then just repeat this output, and then we flatten we just repeat this sequence, then we just flatten the output, and then we use the output or I mean the layer for the output classes, right? So we'll be using the same over here. So we'll be using tf.keras.sequential.conv 2D, and over here what we can do is we have to pass in, I guess this should actually have given me the tf.keras dot, okay, it should be tf.keras.layers.conv 2D and not sequential. So as you can see, this is conv 2D. So like this is how I came to know that since it was not auto suggesting me, so I knew that this is given, like this is giving me a fault somewhere, or I'm actually doing a fault somewhere. So you could be quite sure that this is why the thing is. So again, you know like how to actually check if I'm making an error. So the first parameter or the first argument to our conv 2D function is called number of filters. So what we could do is like I could actually start off with something like 64 filters. So I already hope you have actually revised what filters mean. I mean the mathematics behind convolution 2D or the CNN networks in general. So I won't actually go into details of what filter and kernels and all of these things actually mean, right? So filters, I will be using number of filters as 64, and then I will be using like kernel size of 3 cross 3, right? And then activation function, I will be using this as ReLU. So I hope you're already aware of what activation function is. And then like since it's the first layer of since it's the very first layer of our convolution neural network, we need to give an image target as well. So if I search it, like if I search in the prototype of this function, you will see when using this as the first layer, the model provide the keyword argument input shape tuple of integers for 120, I mean for this kind of thing. So if your image or input shape is 128 cross 128 cross 3, so just use 128 cross 128 cross 3 in the parameter called input shape. So since it's my first layer, I would need to do that as here as well. So input underscore shape. And how do you know which input shape you are using? So just have a look at your train directory. So we have used a target size of 224 comma 224. So that means we are using an input shape of 224 cross 224. So it should be 224 cross 224 cross 3. So these 224 cross 224 is the width and the height of the images, and 3 is for the number of channels. So because it's colored images, so we are having 3 channels. So it's the RGB channel. So that is why we have used 3 over here, right? And then I could use, like once this layer is complete, now I will use a max pool layer. So tf.keras.layers.max pool 2D, just a second, yeah, tf.keras.layers. Max pool 2D, you could see it comes over here, and then I will use a pool size of should be in small, pool underscore size of 2 comma 2, right? So good to go. Then what I will do is, instead of typing this thing over here again, I will just copy paste this thing up, like paste this thing up over here, and okay, just like this. Now I will reduce the number of layers from 64 or filters from 64 to 32, and I will keep the rest of parameters as same, and I will also remove the input shape because now this is not my first layer, right? I will keep the activation function as relu itself, and I won't change that. Again, max pool today is all fine, the layer is all fine, we don't need to change that. And once we have done this, I will again copy this and paste this over here, and now it's 64, 32. Can you guess what the next would be? It obviously would be 16. I mean, this depends on what you need, I mean what you want to choose, but I am using a symmetric kind of thing. So it should be tf.keras.layers.conf2d 16 3,3 activation relu, and then tf.keras.layers.maxpool2d with max 2d pool size as 2,2. And once this is done, I will now use my last layer of convolution, I mean this last layer before flattening this thing up. So it would be 8,8, and rest things would stay the same, right? And now when this is done, what will happen is that since it's an image, right? It's a image, and so that means that it's a how can I say, like I mean since it's an image, we need to flatten this thing up, like to get the output in a kind of 1D shape, or to get it in the form of table. So we have to flatten this thing up. I've already explained the mathematics behind this, so I hope you are aware of what does this means. And I will just use flatten over here. So when is flatten used? Flatten is just used before to use the last layer, or before like you decide to close the convolution layer. So I've decided to close the convolution layers over here, and that is the reason why I have used flat. And now I'll be using a simple layer, I mean a simple dense layer. So it should be tf.keras.layers.dense, and now this dense layer would actually like be like the output that I'm expecting. So I have a number of classes of images as 7, right? So I'll be giving this as the 7, and then I would need to have an activation function in place. So can you tell me what the activation function should be? I mean, you already would have been aware of the activation functions, so just tell me like what the activation functions would look like. If you're thinking it to be a soft max, then you are absolutely correct, and I will just write it as soft max. Okay, and I guess this should be the end of our model 1, but as I can see, I have not imported the activation functions over here. So maybe it's a good idea to change the activation function. So directly something like we'll be using relus only, but tf.keras. Okay, let me just use relu over there, and in case if that is not exported by default, I will actually just change it over there. So okay, so it did work, so nothing to worry about over here then. So then model 1 dot summary, so this would give us what our summary would look like. So you could see we have a conf2d layer in place. So it's a conf2d layer with 224 comma 224, and this is 64, I guess, is coming from, I'm not entirely sure, but okay, 64 is the filter that we have used actually. So it's 224 comma 224 comma 64. Then I hope you already know like how we have arrived at these values. So that was a 224/224 comma images. So to get the value, what we do is it's n minus f plus 1, right? So the n over here is 224. So 224 minus f is like your kernel size is basically your 3. So it's 224 minus 3 is 221, plus 1 is 222. So it's 222 cross 222 cross 64. And then for the max pool layer, it actually becomes the half of it. I mean half if you're using a pool size of 2,2. So 222 divided by 2 is 111. So this is 111 comma 64. And then again like 111 minus 3, it's 101, sorry 108, plus 1 is 109 cross 109. So this is how the mathematics behind it actually looks like. And now what we do require is we have to compile our model. Okay, so before training we have to compile our model. So model one dot compile, and in compile you could see we actually taken arguments such as loss. So in our case, our loss is tf dot keras dot losses dot categorical cross entropy. Then after losses, we take something as an optimizer. So optimizer is tf dot keras dot optimizer dot adam, optimizers dot adam, and then it should be, and the last thing is metrics. So metrics is accuracy, right? And we can just compile this thing up over here. So it tells me could not interpret adam. Okay, I guess we are missing a thing over here, and it did work, right? And now the final step is fitting our model to get the required output. Model one underscore fit is something like, now what do we generally pass in fit? We pass in the x value and we pass in the y value. Am I correct? So as you can see, we have x and y value. But what is x and y value for us over here? So x over here is our train directory, and y for over here is our test directory. Am I right? I mean, y is not exactly our test directory, but because train directory is like the train datagen, which actually contains x and y because it already has the classes. So this train datagen is our complete x directory, whereas this test datagen is our validation directory. All right. So we'll just use model one dot fit train underscore datagen, right? And then we have something called what else we can use over here. Once this is done, call back. So we have x comma y, we don't need to worry about that. Batch size, we will give a batch size definitely, but later. Then we have something called validation data. Okay, so I will just use validation data is equals to, this is called our test directory, and then number of epochs is basically I will be using 5 epochs, and yeah, so steps per epoch is equals to len of train underscore directory, and validation steps we could actually use len of test underscore directory. And I just saw I have made some error. This won't be train data gen, but this is train underscore directory, right? So I hope I'm clear. So this is our x and y for the training thing, train directory. Validation data is our test directory because we will be validating on our test directory. Epochs is 5. This one, how many steps we want it to be trained upon. Then there is steps per epoch, which is like length of train directory. And then there is validation steps, which is len of test directory. And now we'll just pass it on to test our model. So let's see if our model starts testing or not. Something is wrong in our model. So it tells me that fail to convert type of TensorFlow.python.keras losses categorical cross entropy to categorical cross entropy. Okay, maybe we could actually use this. Should work. Let's see. For the first epoch, will take a bit of time. But as I can say, it started giving me 1/5, so most probably that is not an error. But anyways, we need to wait to check if there is, and if there is, we need to go back and see where we have made the error. So let's just wait for some time. Yeah, so as you can see, like this has started training. So we started something with around 12% accuracy, if I'm not wrong, and now gradually we are improving our accuracy, right? So like training this will take a bit of your time. So like maybe just let us just wait till the training gets completed. All right. Shivani, this was the part I was talking about that you have to edit. Like, this training part is approximately taking something about 2.5 minutes to get completely trained. So you would have to cut it like the moment we start training to just when we like we are at the fifth epoch. Is that all right?
Yes, we'll agree.
Also, are we going too long?
It hasn't been an hour yet. Like, how much of the like content is remaining?
It is remaining. I mean, it is remaining. I mean, a substantial part is remaining. However, we have seen them how to create a convolutional neural network. So a good part is done, but improving our convolutional neural network and all of that stuff is actually remaining. So
20 minutes?
sorry.
20 minutes, around 20 minutes.
Yeah, around that.
Okay.
Okay.
Anyway, the duration of actual classes will be 2 hours. So that's
I understand this.
should I post the questions and then
I will just answer the question you just asked me about overfitting, and then you could actually post that more questions.
okay.
Okay, so we are now done with our training steps. And as you can see, we achieved a validation accuracy of 42 and an accuracy of 47% on our original data set. So is this bad? Is this thing is this accuracy bad? Uh, in fact, it's not bad per se, but it's not good either. Why I'm telling this is because let's suppose like we have 7 classes, right? So 100% accuracy, like if you were to divide it or if you were to find the probability, I mean, if it was divided equally, you would have actually done something like 100 by 7, right? So which would be around 13%, if I'm not wrong. So that means like we should have started with 13%. And if we were to just take a guess, right, like if we were to just take a guess on these 7 classes, so we would have actually got an accuracy of 13% in the like in the average case. But now we are getting an accuracy of close to about 42%, which is more than 3 times of what we are trying to achieve. So per se it's not good, because 50% again, like you don't expect a machine learning model to give you a hit or miss chance. You wanted to like build it to the maximum capacity or the maximum engagement that is possible, the maximum accuracy that is possible. So not the best, but not the worst either. So I just got one question sometimes back from one of the students who asked, like, how can we know that if a model is overfitting? Now, first thing first, let's be clear with what overfitting is. Overfitting is basically when your model, instead of learning, it just memorizes the task. What that means is, let's just be very clear with a very practical example, right? So let's suppose there is a student in your class. All right. So this student performs very well on the unit test. Now you'll ask me why. This is because he knows that, okay, like I know in unit tests, these questions will definitely come, or the questions will definitely come from the my class textbook or from the my notes which my teacher has made. So he or she memorizes that complete like notes, and therefore he gets the marks very easily in the unit test. But when there is an external examination in place and no one knows from where the questions will come from, he or she does not perform very well. Why? Because instead of learning, he has actually memorized the content. So that is why the result is not very good. The same is the case with overfitting as well. So what overfitting does is that instead of like learning from the like the data set, it actually like memorizes that thing. Okay, instead of this, I mean, instead of like if it is okay, like okay, this is a picture of pizza, and if this is the exact picture of pizza, then if it comes, then I will credit it as pizza. So it's a sort of this thing. So overfitting can be very easily predicted by like drawing curves. So I will tell you a very short trick to like know like how to predict like overfitting without predicting or without drawing the curves or the training loss curves. But I would suggest you not do that because it's not always the correct option. So when you see your validation loss is actually increasing, but your validation accuracy is actually going up. So you will come to understand that okay, my model is actually like overfitting. I hope I'm clear over here. Like what does that mean is like generally loss should decrease, right? So the more you are correct to the right answer, the loss should decrease. But in case of overfitting, the loss would increase, but at the same time your validation accuracy will increase. So these two are not in sync. So that is why I could tell that okay, it's the case of overfitting, and deep learning models suffers from the problem of overfitting. So it's nothing to worry about. There are specific ways via which we could reduce the overfitting. So this time I actually forgot to draw the curves because I had to save this in a variable called history or something of that sort, but I did not do that. So next time, like when we are building the model, I will definitely do that, which will give you an idea of how to plot these curves. Don't worry about that. So now once we have built our model, like let me just copy this model over here again, and we'll make some changes in this model. All right. So I will just give it the name called model 2 tf.keras. Okay, so now instead of using like these layers, what I could do is, I guess there is one more question. Okay, the question is on transfer learning, but we have not reached over there till this point in time. When the time comes, definitely we will answer like the resource for transfer learning. Don't worry about that. So now I will just increase the number of this filters, like as you can say, this parameter over here in this layer. So tf.keras.layers.conf2d conf 2d, and the number of filters, like I could use something like 256, just trying and testing different things out so that um, we could be sure of what we are expecting. And then input shape is equals to input underscore shape is equals to 224 comma 224 comma 3, and then activation is equals to ReLU. Am I right? And then just copy this thing over here. Don't worry, like if you want to write it in complete sense, you could actually do that. Like I won't stop you, but this will save some of your time if you are copy pasting from the already written layers. So just like this, and I will do something like 128. So 256. Okay, pool size 22, and now because this is not our first layer, I would need to remove it over here. And now instead of going to 8, like I will just delete this and I will just use till 16 years only, correct? And let me just compile this once again now. So instead of 64, this time we started with 256, and then we actually stopped at 16. So compile it here now, and I guess this is giving me some errors. So why it is that? Okay, active. Okay, yeah. So Okay, this is done. And then again, we have to compile this model, which would be model2 dot compiled. Compile will be first thing would be loss, which is tf dot keras dot losses dot categorical cross entropy. Then optimizer is equals to tf dot keras dot optimizers dot Adam, and then the last thing would be metrics, which would be accuracy. Okay, once this is done, I will store this in a variable called history2, the fit thing. So just copy this thing because this thing would actually remain the same. And just change this to model2.fit. All right, and just run this code over here. And again, like, let's see if that improves or not. Cannot guarantee you if this will improve or not, but let's see if it does or not. So we have to wait till our model finishes evaluation. Okay, so we are done with the our loss, I mean, training our model. So as you can see, the accuracy is decrease. Sorry, the losses, validation loss is decreasing. The validation accuracy is increasing. So it's a good estimation that our model is not overfitting and is doing good as well, because again the actual loss is decreasing as well. So in case we decided to train it for more epochs, like maybe 10 epochs, we could have got a better result, but that would have taken a lot of time. So we are not doing this, but anyhow, like, because the question was on overfitting, so let us see by plotting the curves if we could understand what overfitting is. So I've already stored this result in a variable called history2, and now what I will be required to do is I will be required to plot this thing, right? So I will define a variable which I will call epochs, and I will give it a range of 1,5, right? It should be 1,6, because again, the last thing is not counted over here. So epochs is 1,6 ep, which we call it. And now I will use matplotlib.pyplot. I mean, I guess I already have imported matplotlib.pyplot as plt. Yes, so it should be plt.plot, plt.plot. What we would be plotting in the x curve, like in the x axis, obviously that would be the epoch. So this is the epoch, and then what in the y axis should be history. Sorry, actually we have stored this in a variable called history2, it's underscore 2, right? So it should be history underscore 2 dot history, and we'll be plotting the uh, training loss. So train underscore loss, and I guess a color should be fine. So we could give it a color called green, and plt dot plot, it should be ep comma history underscore 2 dot history. There should be train underscore accuracy, and the color could be blue. Let me just plot this now. Okay, it says train loss is not identified. Should not be the case actually. If I'm not making any train underscore loss is not identified. Error. Okay. Okay, I will just print this out to check if everything is intended the same way we have intended or not. So train underscore loss, and okay, it's not working this way. It's 3 underscore 2. Okay, dot history should be working. I don't know why it's not. Okay, let me just check on the official documentation once. Official documentation that works. Train underscore loss. Okay, let me just print it for val underscore loss. So for val underscore loss, this is getting printed correctly, but for train underscore loss or train underscore accuracy, if this is getting printed correctly or not. Okay, I don't know why it's not getting printed for this thing. I guess this is not being stored over here, but anyways, like we could I will need to check over here like why it is not working, but instead of train underscore loss, now at this point in time we could use something like val underscore loss and val underscore accuracy to get this thing working, and just give it something like green and just give it something like blue. Let me just plot it over here. So as you can see, this is the plot that we are getting. So green is for your validation loss, and blue is for your validation accuracy. So do you think the plot that we are getting is correct? I think it is. Why? I mean, what we are expecting, it's not overfitting. Why? Because if you clearly look at your loss should always decrease. So this is the green line. So the green line is going down, that means the loss is actually going to decrease, whereas your accuracy should always increase. Am I correct? So this is the blue line. So your validation accuracy is actually like climbing up the slope. So it's increasing. So your loss is decreasing, your accuracy is going up. So that's a thumbs up, because that is what we intended to do. And we know our model is not overfitting if the two curves actually actually converge at a particular point. And as I can see, like if this model, like if I were to increase the, or maybe just extend this curve to some more epochs, there would be a definite point where this model would actually converge. So that means our model is working very fine over here. So this is not the case with overfitting. However, if there was a case that these two more like these two things would actually be going or separating away from each other, like let's say instead of going down, this would have been going up, and instead of going up, this would have been going down. So they are actually like not like they are not they won't meet at any point. So that is a definite case of overfitting. So this is why like we have to use this. I mean, we have to use a plot curve to understand like what overfitting and underfitting is. So I hope from the question it's very clear key why overfitting and like um I mean, how to identify overfitting and underfitting. So this is all good to go. And now let's suppose, okay, we have like did some part over here, and we can go with image augmentation as well. But let us just now go into transfer learning, right? So go into transfer learning and see like how we could actually like increase the accuracy of our model and what resources we have. So I guess there was a question posted by one of the students that how do we know which transfer learning model to use? Is there any resource hub via which we can get the exact information? Yes, there is a resource hub via which we get the exact information. This is called TensorFlow Hub. So if you just search it on Google and go to this link, so this contains everything that you need to know. So here you could actually go to like it's the repository of all trained machine learning models, and like you could see like there is something for birth, which is NLP, then there is something for object detection, then on device food classification. So like this is using TensorFlow.Lite, like the one we are actually doing. Let's see, this is the food 101 dataset, and just to give you an idea, we will not be using this model, but I mean, I'm just giving you an idea. So there is a definite transfer learning model for food classification as well, which is called the food_V1. So like they have a working demo over here as well. So not working demo, I mean they have a screenshot over here as well. So maybe you could actually like okay, this is a working demo. So yeah, you could actually upload a photo and this will tell you like what this is. So for this, it tells you this is a pastry. I mean, shaker hoti. I mean, that should be the same actually. Not sure, but anyhow, this is how it works. But yeah, we are not using this particular model. So I just need to tell you about what we can use. So I will just use models and data sets over here, and then a TensorFlow Hub. So yeah, as you can see, once we're in the TensorFlow Hub, like what we can do is we can go to our problem domain. So our problem domain is image. And what do we know? Do we need image augmentation? No, we don't. Just remove it from here. Do we need image classification? Yes, let it stay. Do we need image classification logits? No. Do we need image classifier? No. Do we need image feature vector? Yes, image feature vector is needed. Is image generator needed? No, it's not. Similarly, object detection and image pose detection and RNN detection, segmentation, these things are not needed. Just cancel these things up, right? And just use the format called TF2 because we're using TF2. So as you can see, this will give us a preview of all the different models that we have available in TensorFlow. So one is called MobileNet_V2. It's a very popular mobile net. I mean, if you are working on TensorFlow on Android, so a very popular model. Again, you have something called ResNet 50. the one we will be using. Then we have something called image net, mobile net. We have a lot of these things. So this is the efficient net as well. So this is what we have. But anyhow, we'll be using ResNet 50. So if this is like, if we have not used, if we have not used up our time for the entire class, I could actually tell you how to use TensorFlow ResNet 50 model. Otherwise, like, we could stop over here. But anyways, we'll just give you a basic overview. Maybe we could do this in the next class itself. So maybe you're in the fresh mind. So you could see it's a TensorFlow 2 saved model, and okay, this is a good question as well. What is the need to save the trained model, and can't we directly train the model or the process and get the required output? I will just come to this question just as I finish this section. So TensorFlow 2 saved model, it's already available, and you already have a code output in place, like how you could actually use this particular thing. So maybe I can just copy paste it over here and just use this in my TensorFlow network. The TensorFlow network that I am currently making. But then it's not always recommended to do so, because you want your TensorFlow network to be, you want it to modify it, right? And this is not a modifiable network. So you have two types of APIs, if I'm not wrong. These are, I'm not exactly sure of what the terminologies are, but there are two kind of APIs, and this belongs to the second category of API. So it's not a good idea to use this one, and we could actually go back using the classical API way or the classical way. So I will give you a hint in the next class on how to use that in the classical way. But anyhow, if we were to directly use, we could directly use this as well, and this would give us the result as well. But not get into details over here. So let's get back, and there was a question which was, I guess it was related to how, why should we save a trained model, and why can't we directly train it while we are deploying it, and do something like this. So it's a good question to ponder about. The reason for this is actually, you have seen key training, you see, when we train this model, this took a total of about 200 seconds, which is more than 3.5 minutes if I were to take the case study of this particular convolution neural network. So it's it's more than 3 minutes. So while you're deploying this on the website, will you want your user to actually wait for 3 minutes to get the output to any problem? Have you seen this thing in some way? There are many, uh, uh, there are many websites that give your credit card instantly based on your financial data that you input, or maybe they get it from some APIs, right? So they're also based on deep learning models. Have you seen them asking a customer to wait for 5 minutes while they train the model and get back to you to get the output? It does not happens that way. Similarly, when you are using any online proctoring service, and uh, when suppose there is a movement in the camera activity, so do you tell the client that, okay, I'm just there is a movement detected, I'm just training the model, and it will take me about 10 minutes to train this model, and I will tell you if this is a suspicious case or not? So does this happen that way? Obviously it does not, because this is why we actually tell that we are saving the model. So what saving that model means is, we will take up the complete architecture of the model, we will take the complete architecture of the model, and on taking the complete architecture of the model, we will save the weights as well, weights as in the convolution neural network, and then we could use this model directly. So we just have to use this model dot predict function to actually get the output. So we are saving the trained model itself. So it will save us from a lot of future troubles. So that is the reason why we actually like to save a model in general, other than, and not to use it while training, while making some output. But if this was the case with the machine learning model, right? So machine learning models don't take a lot of time to get trained, because they get trained quite fast. They do not take a lot of time to get trained. So could have been the case where it would have worked in the case of machine learning if we are not training the model and just directly like training the model in the runtime itself. But with deep learning, that does not work that way. So this is the reason why we like save the model save the model before deploying it. And now there is one question that may arise more, is that okay, so that means that even if we get more data set or more data, over time, with time, your data will definitely increase, right? So we are actually using a we are actually caching the data set and using the same data set again. We are not like applying, or we are not getting it to be trained on more data. Am I correct? So no, that does not happen. So what happens is that every while or then you may have seen server updation going, or some sort of this notice in the websites where they mention that okay, we will be having some issues. We'll be having some issues connecting to the website between this and this time. Inconveniences will replay. So this is what they do in the server upgradation. So they again train the model on the new data set. The new data points that have been received, and then it's again a better model as compared to the previous model. So this is how that generally works in the like industry concepts. So we are not covering the topic of transfer learning as of now today because of the limited time we have, but I will just tell you how we could actually save the model. So for saving the model, it's very easy. So we'll save this in a file format called hdf5. So I will just use a name called saved underscore model, and it will be model underscore 2 dot save, and okay, so I will just don't need a name over here, and I need a path. So the path would be let me just copy this path only. So copy path, and content, and the name I would be choosing is my underscore saved underscore model dot hdf5. Sorry, hdf5, right? And let me just save the model. So if you see, now the model should have been saved somewhere over here. My saved underscore model dot hdf5. So the model has been saved. So now you can actually use this model directly in your training data set. In your in your content whenever you are using it. So I guess with this we should close our class for the day. The next class we'll have a look at what transfer learning, how could we actually use transfer learning to better this accuracy. And I hope you have got a clear idea of what CNN is and how to use CNN, how to understand overfitting and all of these concepts. So see you in the next one. Till then, goodbye and thank you.